Welcome to an introduction to real analysis. We continue going through section by section. Here we are in chapter 1, section 5, decimal representation of real numbers. So what are we going to talk about here? Decimal notation is a way of writing real numbers, and it's familiar to most people. We're going to formally introduce it. I'll be totally upfront. This way of writing real numbers is not especially important. Certainly not for this course, but most people tend to default to talking about decimals when they're talking about numbers, so we're going to formally present it. Now we think of real numbers through their decimal representation, in other words, a list of digits, and each digit is something between 0 and 9, so it's a whole number between 0 and 9. For a positive integer n, we can find the digits for some capital K so that the number n is something times 10 to the k plus something times 10 to the k minus 1, and so forth, all the way down to something times 10 to the first plus some digit, and each of these digits is between 0 and 9. Generally, we assume that the largest index digit isn't a 0. Otherwise, you would be beginning your representation with zeros. For example, we write 12 as 1, 2, not as 0, 0, 1, 2. To represent n, we write the sequence of digits as just a list of things concatenated against one another. What about decimal notation for rational numbers? So similarly, if you have a rational number x, you can find a negative integer m, a positive integer k, and digits d sub k through d sub negative m, so that x is something times 10 to the k plus something times 10 to the k minus 1, all the way down to something times 10 to the first, times something times 10 to the 0, times 1, times something times 10 to the minus 1, etc., through something times 10 to the minus m. So we will write this concatenation where this division between non-negative indices and negative indices is marked with this decimal point. Not every real number, by the way, can be written in this way. We've assumed that you can make this expansion and it stops, and not every real number can be written in that way, but some numbers can. The irrational number root 2 doesn't have a representation like this, neither does a simple fraction like 1 over 3. So to get a representation for all real numbers, we have to allow infinitely many digits. We have to allow for this thing tailing off here to not stop. So let's talk about these infinite decimal expansions. First of all, we're only going to talk about numbers between 0 and 1, excluding 0, possibly including 1. If we can deal with these by adding a positive integer, we can account for every other real number. So let's take an infinite sequence of decimal digits. So we have a d sub j for every natural number n, d1, d2, d3, and so forth. Compared to the previous slide, I'm not calling this d minus 1, d minus 2, just for convenience. Now let's call capital D sub n to be the sum d1 over 10 plus d2 over 100, and then stopping at dn over 10 to the n. I'm very consciously avoiding terms from series and partial sums. We haven't formally defined those. So we're going to call this the truncation to n decimal digits. Now suppose I add on one more decimal digit. Because I am adding on something over 10 to the n plus 1, and that digit, little d sub n plus 1, is between 0 and 9, I can only make the sum larger. Possibly equal if the digit is 0, but I can't make it smaller. We are not subtracting things. So this sequence of digits represents a real number if x is the supremum of this sequence of truncations. So here's a proposition, 1.5.1. Every infinite sequence of digits represents a unique real number, and for every n, whatever this supremum is bigger than or equal to dn, but less than or equal to dn plus 10 to the minus n, where this power here matches this index there. Okay, part 2, for every x in between 0 and 1, there is an infinite sequence of digits so that we get this representation. So altogether, there's a unique representation so that for all n, we have this strict inequality here and non-strict inequality here. So let's prove part 1. Every infinite sequence of digits does represent something. So begin with an arbitrary sequence of digits. Since every digit is between 0 and 9, certainly, actually summing up the digits is at least as big as all of them being 0 and not quite larger than all of them being 9. The sum on the left is just 0. It's a finite sum of a bunch of zeros. And one may prove the geometric partial sum formula, which will give a concrete expression for the right, being 1 minus 10 to the minus n, which is 1 minus something, definitely less than 1. So no matter what decimal expansion you have, every truncation is between 0 and 1. So for any sequence of digits, because the truncations are between 0 and 1, they're bounded above. So there is a supremum, and that is how we defined this representation. So every infinite sequence of digits does in fact represent something. It does have a supremum. Now, since the supremum is an upper bound on the set of truncations, which are increasing, we know that the sup is bigger than or equal to every particular truncation. Okay, so that establishes this inequality here. Whatever this sup is, it's bigger than or equal to every particular one of them. Now suppose you take a truncation of larger index. Because we have gone further along in our truncation, we can only make the sums bigger, but they all have to be less than or equal to the supremum. Therefore, if I subtract dn here, we get dm minus dn. Well, you take the sum going out to m and you take away the sum going out to n, leaving only the terms from n plus 1 to m. What is the absolute biggest this could be? Maybe all of these digits are 9. In which case, again, using this geometric sum formula here, you end up with a 10 to the minus n. So dm minus dn cannot be as large as 10 to the minus n. So now if I take a supremum over m, I'll end up with an x here, and we get x minus dn is less than 10 to the minus n, less than or equal to because we passed into a supremum, and that establishes the inequality on the right here. Let's move on and prove item 2. So pick some x in the interval of question here. Let's find the first digit. Out of 0 through 9, some of those over 10 will be less than x. Certainly, for example, x is not allowed to be 0, so 0 over 10 is definitely less than x. Maybe 1 over 10 is, and so forth. Out of this finite list, the things over 10 which are less than x, where that numerator is between 0 and 9, pick the biggest one that works, and call that your first digit. Now, if I look at this truncation, we will simply have d1 over 10. By construction, d1 over 10 is less than x. But since it was the biggest numerator over 10 to be less than x, if you add 1 to it, that would be bigger than or equal to x. Now, d1 over 10 is just capital D1, and then you have a 1 over 10 here. So x is bigger than d1, but less than or equal to d1 plus 1 over 10, matching what we have here. Now we have a base case for our inductive procedure. Okay, the uniqueness of d1 is clear. It's the maximum out of that list. Now assume that you've picked a whole bunch of digits satisfying the desired inequalities in item 2 here. Then you've chosen d1 through dn so that the truncated capital D index n is less than x, but if you add 10 to the minus n, that's bigger than or equal to x. Now what's the distance between these two values? It's 10 to the minus n. So pick 0 over 10 to the n plus 1, 1 over 10 to the n plus 1, up to 9 over 10 to the n plus 1, and ask which ones of those are less than x. Note, adding 0 over 10 to the n plus 1 is definitely less than x, so this is not an empty set. So find the largest I you can put here and still be less than x. Pick that to be your next digit. So the maximum definitely exists. By the way we constructed it, the next truncation will definitely be less than x. Good, that's what we wanted. But if I was to add 1 to it, that would be bigger than or equal to x, which again, just as it did in our base case, will give us the right-hand side we wanted here for our next truncation. Now these expansions are not necessarily unique. If we don't require these inequalities, decimal expansions don't have to be unique. For example, 1/2 is 0.5 and then just zeros forever. But that expansion actually does not satisfy the inequalities that we required. If you just look at truncating it here, 0.5 is exactly equal. In other words, your first truncation isn't less than x, it's actually equal to it. So these inequalities are not satisfied for the way we tend to think of decimal representations of 1/2. However, 0.49999 and then 9s go on forever. does actually satisfy these. And if you look at the sequence of truncations, you would get 0.4, 0.49, 0.499, 0.4999, and so forth. What's the supremum of that? 1/2. So 1/2 is represented by this other decimal expansion. So there are exercises that help elaborate upon this claim. The only x that have dual representations, that have two different representations, are those where one ends in all zeros and the other ends in all nines. That's the only way you can have this non-uniqueness, but it's buried in the exercises. Let's look at theorem 1.5.2. The interval from 0 to 1 is uncountable. Okay, this is a duplicate essentially of a proof from the previous section, but we're going to prove it a different way through decimal representation. So let's get proven. Assume to the contrary that you have an enumeration of this interval. Denote d subscript I superscript j as the ith decimal of xj. So for example, if you look at this list and pick out an xj, the superscripts keep track of which x you're looking at, and the subscripts are then which decimal you're looking at. Okay? For the unique representation given by the previous proposition. So because the previous proposition established a unique expansion subject to some inequalities, those are the expansions we're taking for all of our x sub 1, x sub 2, and so forth. Now let's construct a real number. We're going to show that the decimal expansion is different from all of those. So let the digit en be given by 1 if the nth digit of xn is not 1, or 2 if the nth digit of xn is 1. Let's be pretty clear about how we're picking these e's. So in the table to the right, suppose we have x1, x2, x3, x4. Remember, by assumption, this contains every real number, and here are their unique decimal representations. x1 is 0.31513 and so forth. x2 is 0.44196, whatever. They all have unique decimal representations. There they are. So we're going to go diagonally through this table, looking at the first entry of x1, the second entry of x2, and so forth. Then we're going to pick our e's to either be 1 or 2 in a way that guarantees it's different than whatever this diagonal pick is. So x1 first digit is 3. That's not 1, so we make e1 equal to 1. x2 second digit is 4. That's not 1, so we make e2 equal to 1. x3 third digit is 1, so we make e3 2. Then the fourth digit of x4 is not 1, so we pick a 1. The fifth digit of x5 is 1, so we pick a 2. This is how we're picking our e's. Okay, so think back to prop 1.5.1. We've picked these e's to be 1 or 2. Let's make truncations capital E sub n. There is definitely a unique x, which is the supremum. Okay, so this x belongs to the interval from 0 to 1. However, the first digit is either 1 or 2, so it's not 0. The first truncation is either 1/10 or 2/10. The sup can't be 0. Okay, so x is not 0. So now we begin with a list of all the real numbers and their unique expansions, matching the conditions of prop 1.5.1. Remember, we assumed we had this enumeration. But what do we now have? The way we picked our e's, the first entry is different from the first entry of x1. So our list of e's does not match x1. But the second term of e was different from the second term of x2. So e also does not match x2. The third term of e was different from the third term of x3. So our list does not match x3, and so forth. The expansion we've constructed is not in the list. But this expansion represents a real number, and we assumed our list did contain every real number. And we also do not have all zeros past a certain point or all nines past a certain point. Our expansions are just 1s and 2s, so we're not running into a duplication problem. So we did not accidentally make a duplicate of any x, but we constructed a real number not in the list, but the list was supposed to contain all real numbers. Contradiction. Moving right along to prop 1.5.3, suppose you have an x between 0 and 1. It's rational. Here's its decimal expansion. Then the decimal digits are eventually repeating. In other words, there's a capital N and a P, so that as long as little n is past capital N, the nth digit is the n plus pth digit, and this holds for every index past a certain point. So here's what we mean by eventually repeating. We're not actually claiming that the pattern repeats always, just past a certain point. Go past the capital nth decimal. After that point, you get a repetitive pattern. Okay, let's prove it. Suppose you have a rational number, x is p over q, both positive integers. Note, x is from the intervals from 0 to 1. It's not negative. I am totally fine assuming p and q are both positive. As previously mentioned, the only numbers that have two decimal expansions, those two decimal expansions will either end in all zeros and all nines. In either case, the expansion is eventually repeating, and we're trying to show that rational numbers have eventually repeating decimal expansions. So let's assume that we have a unique representation. If it didn't have a unique representation, we already know it's eventually repeating. So x is less than 1 and p is less than q. Okay, x equals 1 has two expansions, 1.00000 and 0.9999999. So that's not the x we picked. So we picked something strictly between 0 and 1, which means that if we write it as p over q, p is actually less than q. Let's recall the division algorithm. For any positive integer q and any integer n, there's a unique choice of a and b, so that n is equal to aq plus b, but b is positive and less than q. Not necessarily positive, sorry, non-negative, and less than q. So we write x as p over q, p is less than q. We apply the division algorithm to the numbers 10p and q. So there's a unique choice of d1 and r1, so that 10p is something times q plus a remainder, and this remainder is between 0 and q, possibly equal to 0 but not equal to q. Now let's define di and ri inductively by continuing this procedure. Okay? Take your previous remainder, multiply it by 10, apply the division algorithm. Take your next remainder, multiply it by 10, apply the division algorithm, and so forth and so forth and so forth. Okay, so we keep constructing our di's and ri's inductively according to this process. So we have x is p over q, both positive, p is less than q, and we've constructed our di's according to this inductive procedure. Here's where how we pick d1 and r1. Having picked a given r, this is how you pick your next d and your next r. Since p is less than q and r1 is bigger than or equal to 0, your remainders can't be negative, it follows p is less than q, this is bigger than or equal to 0, therefore d1 can't be as large as 10, otherwise you would have 10p equals 10q, from which you would get p equals q, contradiction. However, d has to be non-negative. If d1 were negative, then you would have a negative number times q, and then a remainder that is not too big. You wouldn't be able to get all the way up to 10 times p. So similarly, you carry that reasoning forward. Every dn is a permissible digit, bigger than or equal to 0, but less than 10. Note also that dn plus 1 depends only on rn. Okay. Now rn is between 0 and q at every step. So how many choices of integers are there between 0 and q, including 0 and not including q? There's only q of them. These have to be integers, and there's only a finite list of choices, so at some point you're going to repeat a choice. But since the digit only depends on r, and eventually the r's repeat, the digits must eventually repeat. Okay, now we just need to show that the expansion we've created of these digits really does represent x. For any rational, construct your digits according to this algorithm and you will have it eventually repeating. Now we just need to show that this decimal number is actually equal to the x we started with. So let's show that these decimal digits we constructed do in fact represent the x we began with. Now, since x is p over q, I can subtract d1 over 10 from both sides and get this. Now, from this expression right here, if I divide both sides by 10q, here you'll get p over q, aka x. Here you'll get d1 over 10, and here you get r1 over 10q. Manipulate that around, you get x minus d1 over 10 by throwing that over to that side, is equal to r1 over 10q. Now, R1 is bigger than or equal to 0, so this expression is bigger than or equal to 0. But R1 is less than Q, so this expression is less than a tenth. So x minus the first truncation is between 0 and a tenth. What would happen if the remainder is 0? Well, if this first remainder is 0, you simply get equals 0 here, so x equals d1 over 10. Again, the two expressions you can get here are illustrated in a series of exercises in the text, which we've kind of omitted. But if x is exactly something over 10, 3 over 10, 5 over 10, and so forth, your two expressions are that followed by a bunch of zeros, or that minus 1 followed by a bunch of 9s, in which case we definitely have eventually repeating expansions. If R1 isn't 0, then this isn't equal to 0 here, so x minus d1 over 10 is strictly between 0 and a tenth. And if x minus d1 over 10 is strictly less than a tenth and positive, from prop 1.5.2 we would know that d1 has to be the first digit in the expansion of x. So the way we kick-started this inductive construction of digits by picking a d1 to begin with, that has to be the first digit of x. Then we just carry forward that inductive machine. If we assume that we have correctly constructed the first n digits, inductively you would have that x has this truncation plus something over 10 to the n times q. That just comes from here. Okay, there's your 10 to the n times q. Divide both sides by 10 to the n times q. And similar considerations to the previous slide would show if the remainder is 0, you get two expansions, both of them eventually repeating. Otherwise, you are strictly between 0 and the next power of 10. And therefore, you must have constructed the next digit correctly. Again, calling back to proposition 1.5.1. So once you get past the first inductive step, it just sort of carries forward this machine. So not only did we start with x and construct a decimal expansion, that decimal expansion must represent x itself. So for any rational number, we eventually have a repeating decimal expansion. All right, so what did we talk about? Decimal expansion is a way of writing numbers as a sum of powers of 10. It's just a way of writing numbers. It doesn't really talk about properties of the numbers super directly. It's not going to be very important for this course, but because people are very comfortable with decimal representation, it was worth going over it formally. For integers, decimal representation is unique. For non-integers, not necessarily. There are certain rational numbers that have two representations, but in that case, one will end in all zeros and the other in all 9s. Rational numbers have to have decimal expansions that eventually repeat themselves. And the converse is true, but that is an exercise. That is to say, if something has a decimal that is eventually periodic, it must be a rational number. That's an exercise. And we did include an alternate proof of the uncountability of the real numbers, the so-called diagonalization argument through decimal representation. Again, not a very key, central, super important section to this course, but because people tend to like decimal representations, it's worth talking about them a little bit.